we're going to pretty much pick up where we left off last time. And as you recall, where we left off last time was talking about function approximation, which is sort of at the core of many, many learning tasks. And in particular, we talked about, in black, function approximation as a very generic problem, where we have some set of instances x, some unknown target function, the one that we really wish we could learn, but nobody tells us what that function is. Instead, they give us the set of input-output pairs of its input and output. And then we have a set of hypotheses that we, the learner, are going to consider. And last time we pretty much zoomed in on decision trees, which are the special case shown in blue here, where we considered hypotheses that were decision trees. And then we had an algorithm that greedily grew the decision tree to try to fit the data. So if you step back and think about what that algorithm is doing, it's really performing a kind of a search through the space of possible hypotheses. In fact, the algorithm we talked about performed a greedy search, starting with the empty tree and deciding to add some attribute at the root of that tree, and then sorted the training examples based on whatever attribute it chose, and then sorting the examples based on that attribute might, if it's lucky, lead to leaf nodes in the tree which were pure, which had zero entropy. And therefore, we could stop growing the tree at that point because all of the examples are either positive or negative examples. There's no need to make further distinctions. We can just label that leaf node positive or negative. So we talked about that algorithm. And so the way I like to think of it is really that algorithm is searching around in the space of possible decision trees, from short trees to increasingly intricate trees, until it finds one that's good enough, that fits the data. Okay? So in fact, I think that picture of learning algorithms as search algorithms fundamentally is really important. So I want to take a moment. This is, as you'll see through the semester, I have 3 or 4 pictures that I carry around in my head to help me think about all machine learning algorithms. And really, this is the most fundamental picture, so I want to draw it for you. We can draw it together. Let's use a fair color. I recommend blue for my favorite color. Okay. So what's the big picture that we're talking about when we talk about function approximation? So you could think of, as we just saw in that previous picture, you think of the space of all possible hypotheses. So this is a Venn diagram of possible hypotheses. Here's one. It's a decision tree, particular decision tree. That's a point in this hypothesis space. Here's another one. Different decision tree. This is the space of all possible decision trees that the learner is considering. And of course, each of these is just some function. I'll use shorthand. I'll draw very tiny circles that look like dots to you. Okay, so these are all, this is the Venn diagram of possible functions that our learner could consider. And of course, that's determined simply by the representation that it's using. In this case, decision trees. But in this picture that I'm drawing, I could use the same picture to think about any function approximation learning algorithm. It's just that I expanded a couple of those nodes so that we could see we can think about this as decision trees when we're thinking about our particular algorithm. Okay, now, what else do we have in our big picture? Well, we have the instances, of course, the x's. Remember, this set of hypotheses is just the set of functions, let's call them h, that map from x to some y. And of course, in the case of decision trees, each x is some feature vector. Remember, windy, outlook, temperature, stuff like that. And the y is a Boolean variable in the case of decision trees. So we could also think of the Venn diagram of all possible x's, inputs to these functions. Okay. So, and of course, there's a relationship between these two, right? What do those functions do? What do those decision trees do? They label the points in x positive and negative. That's what they do. Right? Given a decision tree, we could apply that to every point in x, and we get a label for every possible example that we're trying to classify. Right? If it's the decision tree, for example, to classify days according to whether somebody's going to want to play tennis or not, then the x's are different days corresponding to different feature vectors. And we could apply any one of those decision trees to any of these points in x, and it would label it positive and negative. So let me just do it this way. Let me say for every decision tree hypothesis, there's some set of examples over here that it's going to label positive. I'll say they're the ones inside that region. And the others it's going to, of course, label negative. It has to label them one way or the other. It's a function defined over x. Okay, so this is the problem setting generically that we're talking about when we talk about function approximation. We have a set of hypotheses that define functions over x. In the case of we were talking about before, where y is just a Boolean variable, we could call it 1 or 0, or we could call it positive or negative. And then for every hypothesis, it gives us a complete labeling of all the examples in x. Okay, so now how do we learn? Well, of course, somebody comes by and tells us that's a positive example there. They might tell us there's a negative example. They might tell us some more. Here's another negative example. Here's another positive example. And if they told us that, then we might say, well, we're happy with this tree that I happen to have drawn out here because it happens to label all the positive examples positive, and it happens to label those two known negative examples negative. And of course, that's what we want, right? We're trying to grow the tree that fits the data. But the astute observer might notice that there could be other trees that, of course, label some other set of examples positive and negative, not necessarily the same as the first tree. But that second tree might also happen to label the 4 training examples correctly. And of course, there will be other less fortunate trees in H that really mislabel those 4 training examples that were provided. And hopefully, our learning algorithm won't output one of those. In fact, you know, the way we defined the decision tree growing algorithm last time, it's guaranteed that if there is a decision, well, I have to be careful. It's not guaranteed. It's a heuristic search algorithm. Right, even though we talked about what a beautiful thing entropy is and what a beautiful thing mutual information or synonymously information gain is, we didn't prove, because we can't, that using that heuristic to grow the tree will necessarily converge to a perfect tree. But I guess, nevertheless, the following statement is true. Even with that heuristic, I guess if we keep growing the tree until we perfectly fit the data, and if there exists a tree that fits the data, then I'm pretty sure we'll get to it eventually, because eventually we will grow, as somebody pointed out last time, we'll grow the complete tree, that if there are n attributes in our feature vector, we'll grow the full tree of depth n, and then there will be one different instance x at each of those leaf nodes, and we'll be able to perfectly classify the data. So I guess we're okay, as long as there's no horrible situation where somebody repeated the same x, and once they told us it was positive and once they told us it was negative. As long as that doesn't happen, then there will be a tree that perfectly classifies these examples. Okay, but back to the main point. So this picture I find very useful for a number of reasons. And one of them is that it helps me keep in mind the single most fundamental problem with inductive inference, which is that, well, let's see. People give it different names. One way to say it is you can't get something for nothing. Some people call it the no free lunch problem. But in a nutshell, there's a problem here that unless we're willing to make some prior assumptions about what H is, or maybe some prior assumptions about which hypotheses, which decision trees are more probable than others, unless we make some kind of prior assumptions, we're toast, in the sense that our learning algorithm really cannot generalize reliably to new examples without some bias. So I want to dig down on that a little bit. Let's see what that really means. First, let me just ask you a couple questions. Let's fill this in the decision tree case. Let's suppose our x's are just feature vectors of Boolean features, x1 through xn. These will be Boolean features. Oh, and let's say, just for the sake of argument, we have 20 features. Okay. So 20 Boolean features, you know, like is it sunny out or not? Is it snowing out or not? Different features that describe our days. So what's the size of x? How many instances are there in x? 2 to the 20. Right. In general, 2 to the n. Okay. 2 to the 20, well, let's see. 2 to the 10 is 1024, so 2 to the 20 is 1,000,000. Okay, so about 1,000,000 examples. Now how big is H? Two to the 20. Right. H is 2 to the 2 to the 20. Why? Because, as we discussed last time, we can represent any Boolean function over Boolean variables with a decision tree. If we have 20 variables, we'll just grow a depth 20 complete tree. And every one of those 2 to the 20 examples, in fact, there will be 2 to the 20 leaves. There will be 2 to the 20 leaves in that tree. And so now each of the 2 to the 20 examples will have its own leaf where it's alone. And now we can go through and we can label every one of those 2 to the 20 leaves, plus or minus, positive or negative, 1 or 0. And we can therefore represent any function we want just by adjusting the 1s and 0s on those leaf nodes. Right? So we have 2 to the x, which is sadly 2 to the 2 to, well, I don't know if it's sad. It's a big number, though. I don't know what 2 to the million is. It's big. So that's the situation we're in. Okay. So now let me ask you another question. Well, before I ask the question, obviously, if there are only 4 training examples presented in this case where we have 20 features, and 2 to the 2 to the 20th possible decision trees, then obviously there are going to be a lot of different decision trees that happen to label those 4 training examples perfectly. Right, that's obvious. My question is, how many training examples am I going to have to provide so that we can narrow down the set of candidate decision trees to just one? You know, if I give fifth example, like maybe this one, now, oh, okay, I just eliminated from the running this decision tree over here, because now it incorrectly labels that negative example positive, so it's out of the running. But don't worry, there will be another decision tree like this one that'll cover some set like this, and so there will still be more decision trees that correctly label the two positives positive and the three negatives negative. So my question is now, how many examples how many labeled training examples am I going to have to provide if I really want the learner to be able to identify a unique decision tree? 2 to the 20. Every one of them. Okay, the only way I'll ever provide enough training examples to end up in a situation where there's only one decision tree that fits the examples is if I label every single one of those 2 to the 20 examples. Right? If I do 2 to the 20 minus 1, if I forget to label one example, how many trees will still be left in the running? 2. And what will be the difference between those trees? Well, they'll make identical predictions for the 2 to the 20 minus 1 labeled examples that they've seen. They'll make the correct prediction, of course. But for the one that we haven't shown it, there will be one tree that labels it positive, and there will be a different tree that labels it negative, because we can represent every function. Okay, well, in fact, we can't even take a vote between those two trees because it'll be a tie vote. So there's no basis on which our learner can, if we say that what the learner is doing is searching around through this hypothesis space for the hypothesis that correctly fits the data, then we have to be prepared for the fact that there might be several hypotheses that correctly fit the data. And if we have a fully expressive hypothesis representation, fully expressive meaning that it can represent every one of the possible functions over x, then we're going to be in the unfortunate situation that we have to see, number one, we have to see all of the examples labeled before we'll only have one function left as the right one. And furthermore, it'll turn out that not just if we leave out one example will the remaining ones have a tie vote, but it'll always be the case. If we leave out k examples, if we label all but k examples, then there will be 2 to the k remaining hypotheses that, in fact, assign all possible permutations of labels over those examples that haven't been seen. And therefore, on any given question that we ask, like, why don't your remaining decision trees vote and tell me whether more of you think this is positive or negative, the vote will always end up a split vote, 50-50. So it's just a very simple counting argument, but you get the idea. There is no free lunch. You can't magically look at a subset of examples and guess the right function and think for some reason that you're going to be right. There is no free lunch. You can't get something for nothing. So if we think about learning, and I think we should think about function approximation, as searching through a space of hypotheses for the ones that will correctly label the training data and hopefully therefore extrapolate to new x's that haven't shown up yet as training data, but that we're going to want to classify in the future, then we've got this problem. And this is fundamental. This is actually one of the most fundamental issues in function approximation and in machine learning. And so what you're going to see during the semester is we're going to try to find ways around this. So one way around it, for example, is we could say, well, we're going to use a less expressive h. What if I don't allow depth 20 trees? You can only have trees up to depth 10 or depth 2. Okay, now I've made a more restricted h. You can only use decision trees up to depth 2. You can pick any 2 out of the 20 features to put in your tree. But we'll restrict it so you can only use trees of depth 2. Now there will be fewer hypotheses. And we won't have to show all 2 to the 20 labeled examples to narrow our hypothesis down. However, what's going to happen then? Exactly. So then we might find ourselves in a situation where the teacher is trying to teach us some Boolean function, some concept, some Boolean function over these x's, and oh, we don't have the tree that'll represent that function at all, because we left out some of the possible 2 to the 20 functions. So if we had a reason to think that the teacher, like if the teacher told us on this exam you will only have to inductively infer trees of depth 3, then we'd be golden. But in nature that doesn't happen all that often. But so there's an example of if we had that if we can make that prior assumption reliably, then that will help us. That's often not an easy assumption to make. Another thing that we're going to do, and we'll rely most heavily on this, I guess, is instead of saying that functions are, instead of using this problem setting where the hypothesis has to be your positive or the function has to label the example positive or negative, we're going to allow it to assign probabilities to being positive and negative. And we're also going to assign prior probabilities to different hypotheses. And by putting those two things in, essentially those prior probabilities of our hypotheses are a way to try to put in some prior assumptions in a kind of soft way. Much, to put in a prior assumption by saying you're not allowed to use trees more than depth 3, that's a very rigid kind of prior knowledge to put in. And it leads to this kind of problem where maybe you won't even be able to find a tree that expresses the function your teacher is teaching. But a softer thing to do would be to say, all other things being equal, try to find a tree of depth 3. And if you can't, then okay, you can try 4. And if you can't, then you can try 5. So that's a more graded kind of constraint we put on the system. And in fact, if we put prior probabilities over all the hypotheses, just a distribution of priors, then that's a nice generic way of being able to put in information that lets us deal with the fact that we want to use completely expressive hypothesis representation. When we know we can't get something for nothing, there's no free lunch, we're not going to be able, if we don't bring in an additional inductive bias of some kind of initial biasing assumptions of some kind, then we won't be able to label any of the unseen examples. And so putting prior probabilities on the hypothesis space is a very nice, well, probably the dominant way of dealing with this issue. Okay. So 10 years from now, when you may have forgotten some of the details of this course, not most, the one thing, if you only remember one thing from the course, you should remember this picture and the amazing fact that inductive inference is impossible unless you make some additional assumption in the form of some initial inductive bias. Okay? All right. So that really is important. All right. So now let's come back to decision trees and see, well, in a practical sense, how are we going to make our decision tree learning algorithm deal with this issue? That it's searching around in this space of decision trees that is completely expressive. And we described a particular greedy, grow the tree from the top down kind of search algorithm. And then we said it was going to terminate when? We said it was going to terminate as soon as it got to a tree that perfectly labeled the examples. Not a bad stopping criterion, but given what we just said on the previous slide, you're probably thinking to yourself, well, that's just one of many, many, many decision trees that it could have come up with that would equally well perfectly classify the labeled data. So why should it be a good idea to use this particular strategy? So what do you think? It's simple. Okay, it has that going for it. I like your. It's easy to implement. My philosopher friend Kevin Kelly, some of you may know him. He's a professor here in the philosophy department. He would not like that answer very much, though.
Also the result is simple.
The result is simple, and it's easy to inspect for us humans. I would agree with that. Yes.
I think it makes less assumptions about data that you don't have. So it's not, if you go after a less acceptable tree, you're leaving unknowns purposefully in the tree. Like it's going to pull out data, and that way, if you were to add more, it would assume that you are making decisions based on variables you don't necessarily know.
Yeah, that's good. So you say roughly what you're saying, to paraphrase, is you could grow a more detailed tree, but you'd be just making stuff up without any data to justify it. At least the things that are in this tree when we stop they were added for a reason. They weren't just arbitrarily made up. That's okay. So I don't disagree with those kinds of arguments, but I get nervous that if I had to talk to Kevin Kelly about that, my philosopher friend, he'd punch me in the nose or something like that. He wouldn't like it. So there is the first person to try to come up with this kind of justification that we know of is William of Ockham, who said, well, all other things being equal, we should prefer the simplest hypothesis. And so that's a kind of justification that we might give for doing this. And people have debated for centuries since he came up with this in the 1300s. Since then, a lot of people have debated about whether there's any justification for that or not. And I'm of two minds about this, so I thought I'd put up both the pros and cons about this. So I guess we could say, if the question is why should we prefer short decision trees to longer ones, why should we stop as soon as we find a tree that does well enough and not just add some more edges to it that won't change the fact that it fits the label data, but might change how it labels unseen examples. Let me do it this way. So here's some arguments in favor, the kind of common arguments in favor. Statisticians sometimes try to justify it this way. They say, well, sure, if you have 20 features in your feature vector for x, you have 2 to the 20 x's and 2 to the 2 to the 20 hypotheses, decision trees that you could have. And if you only have 100 training examples labeled, there's kind of a high probability that you could find some tree that fits those data. But if you only restrict yourself to only considering short trees, then you have many fewer trees, not 2 to the 2 to the 20, but many fewer, 2 to the 2 to whatever depth you allow, for example. Actually, that's a lower bound. think about that in the shower. And so it's not as likely that if you restrict yourself to only depth 3 trees and you have 1 million labeled examples, or 500,000 labeled examples, it's not as likely that you would happen to find one of these fewer short trees that fits the data. And therefore, you could be kind of justified in thinking that, oh, well, it must be capturing some regularity. There aren't that many trees of depth 3. If I find one of depth 3 that works, it's less likely to be a statistical coincidence. On the other hand, it's more likely if I allow myself depth 18 trees, it's more likely that I'll be able to find one that fits the training data, but it's a coincidence in the sense that it won't do very well on labeling the other unseen as of yet examples. So that's the kind of argument people give. And I'm not convinced by that argument. It seems incomplete, to be polite. But I'm faced with the following empirical evidence. People do this. People train decision trees this way, and it works. And it works better than if you, let's say, pick the longest tree that's consistent with the data. So there must be something going on. So there must be something going on. So let me tell you my argument opposed, and then what I think might be going on. So here's my argument opposed. This is why I'm skeptical about Occam's razor and about the idea that we should a priori think that the shortest decision tree is the best one, or the shortest one consistent with the data. My problem is, I imagine there are a lot of, if the argument is that there are only a few short trees, then I can make up a lot of ways of defining smaller hypothesis spaces. Right? I could only, well, I'm only going to consider decision trees with a prime number of edges. There aren't so many of those either. And I can therefore apply the same argument that's being applied to justify short trees, namely that there aren't so many of them, so it would be less of a statistical coincidence if we find a short tree, because there aren't so many of them. Well, I could apply the same argument here. There aren't so many decision trees with prime numbers of edges. Maybe I'd be right. I haven't actually tried that experiment. It's harder to implement. So my problem is I don't see what's so special. I can kind of believe that if you have a smaller hypothesis space and you happen to find a hypothesis that fits the data well out of that, then there's some kind of reason to think that it's not a coincidence, that there's really some regularity being captured. But my problem is I don't understand why short trees should be the way that we define small hypothesis space. Yes?
In the approximation theory, then, people often use the information criterion AIC, BIC.
Yes.
You know, in that case, then, given the same accuracy, then it favors the lower order of models. Does that make sense to think along that direction as well?
It's right. So the comment, if you didn't hear it in the back, is, you know, in many fields like in curve fitting and in information theory, people often prefer, say, if you're fitting a polynomial to a bunch of data, people often say, use the lowest order polynomial that fits. Don't try to fit a 27th degree polynomial if a 3rd degree polynomial will do it. It's the same kind of argument. And just like decision trees, and this heuristic for decision trees, the empirical evidence is that's a good idea. It works. My problem is I don't believe the arguments that I hear for why it works. So experimentally, I have to say, this is, I use this idea when I design learning algorithms. But what I'm doing is I'm trying to get us all to think about why on earth would that be a good idea. Right? And generally the argument, and the same thing for lower order polynomials, the same argument, there aren't so many functions that are well described by lower order polynomials, and therefore it's more of a surprise if you can find one that actually fits the training data, whereas it's less of a surprise if you can fit a very high order polynomial to the same data. And because it's more of a surprise that you can fit it, you have some basis for thinking it will generalize to future examples that weren't in your training set. And so I buy that argument. It's just that I don't know why short tree should be the way that we restrict the number of hypotheses, or lower order polynomials should be the way that we restrict the set of polynomials. Okay, so I don't want to spend the whole lecture talking about this, but I think it really, I'm sometimes surprised that people in machine learning don't lose more sleep over this. I lose a lot of sleep thinking about this. I think it's a kind of fun, if we don't understand this, but we're building programs that are generalizing from examples, that are doing inductive inference from this data to make predictions about data we've never seen, and we're just not even bothering to think about this issue, then we're like missing the main question. Okay, so now I have to tell you what I really think. What I really think is this heuristic works, and it tends to work. Think of it this way. Suppose you were the deity, or you were designing beings in a big sim game, and but you're restricted. Your beings that you could design only had small brains, and so they couldn't do very much, and they could only deal with small hypotheses. Their brains weren't so sophisticated, so they could only represent small hypotheses. You're kind of stuck with that. Now you get to design the rest of the being. So what would you do? I think what you'd do is you'd try to give those beings sensors that had the property that hypotheses that were small and used the features you could observe with those sensors would happen to be good ones in the universe that they lived. So maybe in this scenario, the reason that short trees work well is that the way we define our features, the way we naturally think of features, has the property that small combinations of those features capture good regularities. Right? Another way to think about it is, imagine there was a Martian who came to visit our classroom, and that Martian had different sensors. Each of their sensors, like each of the attributes we saw, they saw some other attribute that was a combination of 7 of these, attribute 1 plus attribute 2 squared plus attribute 4 cubed minus attribute 5. That was one of their features. Now, if they tried to use Occam's razor and grow the shortest decision tree, they'd be in a sorry state. Because, of course, that would be a very long decision tree for us. See what I'm getting at? It's actually, the Martian is another reason why I'm skeptical about this argument in favor of Occam's razor. Because I can design other beings where the tree that was short for me is very long for them, and one that was... Okay? So what I really think is maybe evolution has helped us. I worry about how we ourselves can do inductive inference. And sometimes I think maybe evolution helps us to, by giving us sensors and low-level perceptual processes that allow us to find features that happen to satisfy Occam's razor because we have such small brains, we only use simple learning algorithms anyway. Okay. So that's what I really tell my friend Kevin Kelly when we get into these discussions. And then he doesn't punch me, he just... Okay. But it's a serious issue. You should lose some sleep over this. So if you wake up in the middle of the night, think about that problem and think about it. All right. decision trees. So how do we fix our decision tree learning algorithm to really work? So I want to look at overfitting issue for decision trees in a slightly, from a slightly different angle now, which is this. Here's the tree that we learned last time, and it was consistent with those 14 training examples that we put up on the slide. What I want to say here is let's consider adding a 15th training example, which is this feature vector, which is labeled play tennis equals no. So now imagine that we have this 15th training example. So, well, obviously this tree is going to do the wrong thing with that because this example is sunny, so we'll go this way, and the humidity is normal. So it'll go this way, and it'll label it a yes, but we've told it it's a no. So this tree would mislabel that example. And so if we were to include this 15th example in our training set, we would obviously get a different tree from this one. And one tree we might get, you know, could just not make that a leaf node anymore. It would just make it a node that chooses one of these other two attributes, like maybe temperature. So now we could have temperature, which could be hot, in which case we'll now say no. And, or it could be cold, in which case, well, we don't really have any basis. We could just guess. What do you think, yes or no? Yes. Okay, I heard a yes. All right. You see, we're just making up stuff. So anyway, if we had that additional example, we might end up with this tree. But now, you know, we were just guessing about the label of this.
Actually, it's not a guess because you labeled it before as yes, so there was a reason.
Oh, okay. I'm sorry. So I stand corrected. We did label this before as yes, meaning those other 14 examples that came down this path had a yes. And so it could be that they were temperature equals cold, in which case that really should be a yes. So I stand corrected. Thank you. Okay, but so there's one tree that would now be consistent with the data again. But the other possibility is this one. Instead, we could have done outlook. So instead of making this tree, we could have instead had an outlook feature here. Or I'm sorry, wind. Oh, I get to use, I have an eraser on here. It's really awesome. Okay. Thought you'd like that. Wind. Okay, so instead we could have wind, and we could have strong, weak, and we could do something there too. So you can see that there are a couple of different trees that could have come out of adding that new example. And so the point of doing this is to, again, make you nervous about the fact that we don't really know which of these, let's say these two trees, the one that uses temperature as the attribute here versus the one that uses wind here. We don't really know which of those two is the right tree in terms of which one would do better on future examples that we haven't yet seen. Both of them do equally well in cleaning up this 15th example, making things work again. But it's just that we really don't know which feature is the right one. And so this kind of problem, and it's directly traceable back to our big picture, right? These are just two more of the decision trees in H that could perfectly fit this small sample of labeled examples. So a very real, very practical problem in decision tree learning is overfitting. What does overfitting mean? What it means is that we pick a hypothesis, in this case a decision tree, that does very well on the training data and terribly less well on the future data that we're going to have to be classifying in the future. Or to be a little bit more precise, I define overfitting this way. So suppose we have some hypothesis that we choose, H, and we have its error over the training data. In fact, here we're talking about an error of 0 over the training data. We don't make any mistakes. But we'll say that outputting hypothesis H overfits the training data if there's some other hypothesis we could have output, H prime, where H prime actually does a better job over the distribution of future examples, has a smaller error than H, the one we're outputting, but it looked worse on the training data. And there are lots of examples of this. And if you go back to fitting low-order polynomials, you'll see it. If you fit a third-degree polynomial to some noisy data, you won't perfectly predict all the points. And you can do better if you use a 27th-degree polynomial. You'll have a smaller training error. But then when you go to take either that third or 27th order polynomial and try it out on some new data, you'll generally find the third order one has smaller error over the future data. So it's overfitting in exactly this sense, that we're outputting hypothesis H, which has a smaller training error, but sadly has a worse, I'm going to call this the true error, the worse error over future examples, the true error over the entire distribution of examples we're going to see from X. Okay, so that's overfitting. And it happens in decision tree learning, and it happens in many, many, many of the learning algorithms we're going to talk about. And here's some evidence of this. This is from a decision tree learning algorithm that I wrote and created this plot from. This was from a diabetes classification task, classifying patients according to whether they have a particular type of diabetes. And what I'm showing here is the number of nodes in a decision tree as the tree is being grown. And I grew the tree's breadth first in this case. So I fleshed out all the level 2 nodes before I went on to level 3 nodes and so forth. But here you see the size of the tree in terms of number of nodes. And that top curve is the accuracy of the tree on the training data. And you see as I add more and more nodes, it gets more and more accurate on the training data. That would have to be if I had a correct implementation of the decision tree growing algorithm we talked about. You can easily prove to yourself that every time you add a node to that decision tree according to that algorithm, your accuracy is going to increase. Yes?
What we did in that last example when we were overfitting, where we added something to the decision tree we already have, that's different from what we were doing before, where we already had all the data, right?
Yeah, that's a good point. So when I was saying let's add a new node to the tree, yeah, if we did that incrementally after we already had the first tree, that's a different algorithm. But what I should have said, to be more correct, is imagine we ran that same batch processing algorithm on a set of 15 instead of 14 examples with this new one included.
So this is as if you had all the data from the beginning of this plot?
This plot, we had all the data at the beginning, and I'm just growing the tree breadth first. And so what you see is here on the training data, we do great, better and better as we grow the tree. But on a separate held out set of test data, which wasn't seen by the trainer, I just took the tree at every stage during the growth and tried it out on this test set. And what you see is the accuracy got better for a while, and then it got worse. It's exactly overfitting, right? So at this point, we had a hypothesis where the training error was very good, the test error was very bad. Training accuracy was very good, the test accuracy was very bad. Is there another tree that could have, or is there another hypothesis that could have done better? Sure, this one over here. Has worse training error, but it actually is has a better true accuracy over the held out data. So this is exactly the kind of overfitting that we run into if we try to use this kind of algorithm in practice. So what do we do? So what should we do? generally we have two choices, these two. We can try to build a different termination criterion into the algorithm. Let's only grow the tree until, let's not go beyond leaf nodes that have fewer than 3 examples. We can put some statistical test in there. Let's only split up a leaf node if it passes a chi-squared test for whether all these examples come from the same distribution. Or whatever. We can put different heuristics, different statistical tests to say, let's not go all the way until we have perfect classification accuracy. Let's put a statistical test in. If we fail that test, we won't grow any further. And people have tried that. The other thing we can do is grow the tree as we are until it perfectly classifies the data, and then post-prune it using a held-out set of data. In practice, which of those works best? The second one. I was surprised when I learned that, but it's true. And generally it's because the statistical tests that we try to apply, like for example, if you use a chi-squared test to decide whether to split the node, that's a conservative statistical test. If it says, yes, split it, then you probably should. But if it says no, well, it might be wrong. So it's a conservative test. So in practice, it turns out nobody's come up with a good statistic for deciding as you're growing the tree that you should stop here. In practice, a more practical solution is go ahead and overgrow the tree in a sense, and then use some data that you held out from the training data to prune back the leaves of that tree using that held out data to guide you as you prune it back. And how would you use the held out data? Well, the obvious thing to do is you'll use it by saying, well, should I prune back this leaf node to the node above it? The answer is going to be yes, if doing that improves the performance on the tree on not the training data, but the held out data. And if it does, then you will. So that leads to this thing called reduced error pruning as a standard way of doing this. So let's look at it. When we get our data, we split it into what we'll call a training set and a validation set. We'll hold out some of the training data. Call it a validation set. Create the tree using the training set only. We'll grow the tree until it perfectly classifies the training subset of data. And then we do this pruning. Evaluate the impact on the validation set of pruning each possible node in the tree. So, in other words, look at every node in the tree and ask, should I make this node a leaf? And then you just pick the leaf. If every one of those questions, the answer is no, if you make this a leaf, you'll do even worse on the validation set, then you stop. Otherwise, you greedily pick the node which gives you the best improvement in performance on the validation set, and you make that a leaf, and then you iterate. Yes?
So what's the motivation with pruning instead of picking a different model? Going back to your set of H and picking a different model that fits.
The problem is, so the question is, why don't we just pick a different model, a different H, instead of doing this pruning? And the answer is, usually we don't know what to use instead. If we're using decision trees, we could, for example, say, well, let's only try trees of depth 4, but we kind of don't know.
I mean, I know we're having a discussion about overfitting, and that's probably the answer.
Mm-hmm.
But don't you want as much information about the real world as you can get? And if, in this case, why you're holding out a set of some information about the real world and pruning back to say, okay, well, let's make our model more general. This is preferable in practice than saying, let's go ahead and get all the information we can get about the real world.
If you can go get other information about the world that lets you know, say that some attributes are more likely to be relevant than others, then you should absolutely do that. But assuming that the only information available is the training examples, then this kind of pruning gives you, for example, more flexibility than if you said, I'm going to consider trees up to depth k. Right? Because now you can end up with trees that maybe go very deep in some areas and not very deep in other parts of the tree. Maybe I'm not sure I'm understanding your question, but when you say use another model, I'm not sure what example you have in mind.
Well, what I'm saying is that you chose you took the data that you had, you divided it into a test and a training set, and you took your training set and picked the best model with this, and we completely filled out the tree in this case. And then we're going to go back in with the other data and prune it back and say it made a mistake here. Let's prune it back a little bit. And you end up with a more generalized model, I think, is the goal of this exercise.
Well, a more accurate tree is what we're after.
According to the data that you had, to this test data.
Right.
But you could look at it as you had data about the real world that you divided and put some aside to test how well you did. Is it not better to just go ahead and grab all the data that you had?
I see. Yeah.
In the beginning, because now you know more about the world or whatever you're trying to model.
Yeah. So there are many ways of dealing with this. This is actually the standard way. Another approach that some people take is just train a whole bunch of different trees using different subsets of the training data, and then let those trees vote. There are techniques that we'll talk about actually later in the semester called boosting and bagging that basically involve resampling the training set. But if what you're after is, let's say, one decision tree as output, then this is kind of the best way that we know how to do that, to get one tree. And often you'd like one tree if you want it to be human inspectable. In practice, people often find that you can do better if you just grow 100 different trees and let them vote using different resamplings of the data. But we'll get to that later on in the semester. Yes?
Is there any statistical basis for where this pruning comes from? When you're looking at it from a statistical standpoint, you could say getting a random subset of the data might be a way of trying to get the most assuredness of creating a general tree to fit data. But it seems like when you already have a set of data, that there's really, I'm not sure where you can get any assurity that even with cutting that data up and saying this is training or testing data and this is validation data, how that then, taking that and applying it to examples thereafter would make it more accurate to do pruning with any random subset.
Yeah. So the question was about what's the relationship between this and statistical estimation theory? And the answer is this is basically, you can think of this as an estimation problem. We're trying to estimate the tree, the function, from a sample of its input-output pairs. And so in most statistical estimation problems, statisticians talk about bias and variance as the two problems we confront. And this is exactly that. The reason we get overfitting is because of variance. If you've taken a statistics course, this is variance in the data is killing us here. And there isn't any, well, we have to be, the notion of statistical bias is a little bit different from what we're talking about here. But essentially, there's a bias variance issue in estimating functions from data. That's the way a statistician would say it. And they're capturing the issue that's very similar to what we talked about when we said, well, if we can represent all possible functions with our hypothesis representation, i.e. we have an unbiased representation for functions, then we're getting killed by the variance. There's so many functions that we can represent that we just might pick one that happens to fit a statistical coincidence that shows up in our training data. We can address that by paying a higher bias cost using, say, only trees of depths 4, and have a smaller variance term in our error. And we'll talk later about that. So I need to move on because this is a great discussion. Sorry I have to do it, but we need to move on today. So, okay, so let's look at this reduced error pruning. The effect of this is quite good. Here's a typical case, and this is the case we were just looking at where, remember, we had this overfitting problem where the training accuracy was very good, but the separate test data we did very poorly. If we use that test data instead as the validation set for our pruning, then after we grow the tree all the way up to 95 nodes, we apply our reduced error pruning, it takes us right back to this point, which is a great point to be at. Because as you can see, on the original test set, not the training data, that is kind of the size of the tree where the out-of-sample test, the test data accuracy, was maximized. So this is a typical kind of overfitting problem and a way of dealing with this. The idea of pruning the tree is kind of a special case of the more generic idea, which is if we're afraid that we're going to overfit, meaning that we're going to happen to drive our hypothesis to fit some statistical coincidence that happens to be in the data, then a good way to prevent that is to split the data up, train on only a subset, and then the part we held out we can use as an unbiased sample of data for estimating the true accuracy of this hypothesis that we're formulating. And it'll be an unbiased estimate because it's not part of the training data. It wasn't used to grow the tree itself. It's just this unseen by the learner random sample, subsample of the data. Okay? So you'll get a chance to experiment with this a little bit yourself in the homework. So that's all I really want to say about decision trees. And of course, we really are using decision trees here as our first case study of a function approximation algorithm. But here are the main things you should know. So we talked about what it means to be a well-posed function approximation problem. We talked about learning as a search problem. In fact, in a sense, it's an optimization problem. And in the semester, you'll be amazed by the end of the semester how much it feels like you're in a course on optimization. Because how did we formulate the problem of learning? We said the learner has a representation for functions, decision trees in this case, and that representation for what it can learn defines the virtual space of all possible learnable functions. And then we basically said we're going to design an algorithm that searches through that space of possible functions to find the one that optimizes this criterion. And what's the criterion? Fit the data. Then later we hedged. We said, well, maybe fit the data isn't quite what we want. Maybe it's fit the data and then optimize your performance on the held out validation set by post-pruning. In fact, if I could choose between the two, I'd choose the second one now because of that overfitting issue. But the fact remains, a good way to think about what we're doing here is we're formulating the learning task by making up a search problem with an objective to be optimized. And in this case, the search strategy was greedily grow the tree until essentially climbing higher and higher according to that optimization objective. And through the semester, we'll be talking about a variety of learning algorithms, but many, many of them will end up characterizing exactly this way, as an optimization problem where we'll define some representation for functions. It won't always be decision trees. It could be a polynomial of fourth degree. That's a representation for functions. And we'll define some kind of, and that'll define some space of all possible fourth order polynomials. And then we'll make up an objective function. Maybe it'll be minimize the sum of squared errors in the fit to the data. Or maybe it'll be find the most probable hypothesis given the data. And then we'll talk about how to derive algorithms that achieve finding that optimum. And we'll talk about cases where the algorithm can provably obtain the optimum, and other cases where the best we can do is a heuristic search, which is what the decision tree algorithm is doing. There's no guarantee that this algorithm, the one the decision tree algorithm we talked about, there's no guarantee that it's going to find the optimal. So I spent a little bit more time on decision trees than I would have if it was just telling you about the decision tree algorithm. But really, I think it's just a great case study for thinking about what it means to approximate a function from a sample of input-output pairs of the function. Okay. So we have about 10 minutes left, and I want to make a start on our next topic. Our next topic is very brief. It's just a refresher on probability, because I know that you've all had some kind of background in probability and statistics, but if you're like me, after a few years that kind of gets rusty and you appreciate a quick refresher. So we're going to do that, and during the recitation on Wednesday, we'll go into, that'll be another chance if you want to come to the recitation Wednesday to revitalize that potentially rusty probability knowledge you have. Okay. Also, you'll see here I'm going to jump by some slides. In fact, I'll make a habit in the class of putting some extra slides in that have other issues you might want to think about. There's some interesting questions to think about decision tree learning. You're welcome to peruse and think about those on your own. Okay. So, review of probability. There's some good reading I very strongly recommend as a quick way of refreshing yourself on this. And many of these slides that I'm using here I've stolen from other people who have done similar reviews. So the problem of induction, David Hume has this thing about many years ago, a treatise on induction. And for a long time, people were quite confused about how to think about probabilities. These days, I think we have a pretty a more sophisticated view than David Hume did. And here are some of the things that you should be familiar with as we get into week 2 of the course. So if these look strange to you, you should go back through those readings and swap them in. But, I guess there are a couple more. But let's just start at the beginning. Random variables. So we're talking about our examples, x as being this feature vector. Secretly, whenever I think of that, I think of x is just a random variable. It can take on, it's a vector of several random variables, and each of those can take on some value. And so when I think of the space x, that little Venn diagram, I think of a probability distribution over that space x. And I can still draw the same Venn diagram, but I think for each of those points in x, there's a little probability associated with that. And in the world that we encounter, like if it's classifying days according to whether we'll play tennis, there's some natural probability distribution on those days. So think of day as a vector-valued random variable, and there's some unknown, to me, distribution on days that we'll encounter. And in general, we'll say A is a random variable if it denotes something we're uncertain about, or I think of it as the outcome of an experiment we could repeat. Right? So I could, for example, pick a randomly, A could be whether a randomly drawn student in this room is female. So I could just go, student number 43, we could count 43 from the beginning and see if it's female or male. That's a random experiment. Then I could say student number is 72, and we don't know. But if we did that over and over, repeated that experiment with me choosing a different random number each time, then we'd get some distribution. With some probability, the answer would be yes. With some probability, it would be no. The random variable is the outcome of that repeatable experiment. So I also can think of there being a set of possible worlds, or an event space, each of you being an event. And then I can think of the probability of A as just being the fraction of possible worlds in which femaleness is true, or the fraction of times that A holds if I repeat that experiment. So probably the probability that a randomly drawn student would be female looks to be around 20%. Okay, so random variable, simple idea. I'm going to go quickly through this. But I put more on this slide so that you can follow this at your leisure. Very nice way to think about random variables and probabilities is in terms of Venn diagrams. I think about a lot of things in terms of Venn diagrams. But the sample space is the set of all possible worlds, as shown there as a Venn diagram. And then we can say, well, A is true in a subset of those worlds. And the probability of A is just the area of that red circle divided by the area of the blue square in which it lives. The fraction of the event space in which A is true. If you think about things that way, it makes thinking about probabilities very intuitive. Now, there are some axioms that define probability. They're very simple axioms. Probabilities must be between 0 and 1. The probability of true must be 1. Probability of false must be 0. And the only really interesting one is this fourth one, which says the probability that random variable A is true or B is probability of A plus the probability of B minus the probability that they're both true. And how could that be? So suppose here's my event space, and here are the parts of it for which A is true. So we could think of that fractional area as the probability of A. Suppose here's B. Of course, there are some worlds in which both A and B are true. There are other worlds where only B is true and not A. Others where only A is true and not B. Somewhere neither is true. And what is the probability of A or B? Probability of A or B is all this stuff. Right? And what's the probability of A and B? That's this part. So this makes perfect sense, right? This is saying the probability of A or B is just the sum of these two areas, but oops, we double counted this thing in the middle, so we'll subtract that out. Right? So so these kind of Venn diagrams make it easy sometimes to think about probabilities. Oops, I wrote all over Di Finetti, very famous guy. I didn't mean to diss him. He showed that if you don't believe those axioms, you can lose a lot of money. So, very interesting thing. Those four simple axioms, if you do probabilistic reasoning according to a system that respects those axioms, and I don't, and we gamble, you can take my money. So in other words, there's something about these axioms that's pretty important and should not be ignored. All right. Okay, so I'm going to jump over some of this trivial stuff. We can prove, you should be comfortable proving very simple things from these axioms, like you should be able to prove that those axioms, which I've repeated up there, entail that the probability of not A is 1 minus the probability of A. Of course that's true, but you should be able to prove it from the axioms. I even give you the proof. But it's even more obvious with our Venn diagram, right? The probability of A is just 1, which is this whole area, minus the probability of not A. They have to sum to 1. Here's another one. The probability of A is the sum of the probability of A and B and the probability of A and not B. And again, we could write that as a theorem, but it's kind of obvious if you think of our Venn diagram again. The probability of A, here's not B outside here. That's just going to be the probability of A and B plus the probability of A and not B. And there's a proof. Let me skip through a few of these. Multi-valued. So random variables don't have to be just true or false. They don't have to be Boolean valued. They could be multi-valued. And let's just zoom. Yeah. Let me do 2 slides and then we'll quit. We can define conditional probability, the probability of A given B. And this is actually really important. Because, so for example, we might be interested in what's the probability. Suppose I define play tennis as a random variable, and humidity and temperature and windiness as random variables. The event space is the space of all possible days. Every day that I wake up and look outside, I have a new random run of this experiment, a new random draw from my event space of possible days. And so now all those things we were talking about a moment ago, they're all random variables. I'd be very interested in the probability of play tennis given that humidity equals low and temperature equals high and windy equals and so forth. In fact, when we're talking about function approximation, that's just a special case. We were talking about learning deterministic functions, but we could learn probabilistic functions. So we could learn the probability distribution, the conditional probability of play tennis, given the features that describe the day. And that's why this probabilistic stuff is going to be so important to us. In fact, much of function approximation, we're going to be learning probabilistic functions. And you can think of those as conditional distributions. Okay, I don't want to get into the habit of running over, so we'll stop here, pick up next time. Hey.
So we talked about the post-pruning way to